He's a senior space systems engineer with experience in space mission and architecture formulation and spacecraft conceptual design. He leads center-wide and agency-wide teams, including near-Earth object mission, near-Earth asteroid destination for NASA's human spaceflight architecture teams. Please welcome Dan Mazanek.
Thank you, Sarah. Can folks hear me okay? Does that sound good? Okay. Good afternoon. Again, my name is Dan Mazanek. I'm in the Space Mission Analysis branch in the Systems Analysis and Concepts Directorate here at Langley. And I'm going to give you an overview. I got 15 minutes to do 15 slides, so I'm going to go pretty quickly. We've got time afterwards to answer questions. But I'm going to go through basically an overview of the Asteroid Redirect mission, otherwise known as ARM. And in specific, I'm going to talk a lot about option B, which is the robotic boulder capture option that we've been focused on here at Langley and leading that part of the trade space. So quick overview, and Keith discussed this a little bit, but just to show you, basically the Asteroid Redirect mission is made up of 3 parts: the identification, the redirection, and the exploration. The identification, obviously you have to find targets, you have to track them and get their orbits sufficiently well enough known that you can actually visit them. And a key aspect is actually characterization, is to know what you're actually going to, because asteroids vary in all shapes and sizes, all compositions, all spin rates. So that's an important part, and we'll talk a little bit about that with the different options. The robotic mission is focused on redirecting either a small near-Earth asteroid, something about 7 meters, but somewhere probably between anywhere from 3 to 10, or capturing and redirecting that to a location in cislunar space, what we call a lunar distant retrograde orbit is the current destination that we're looking at. It's a stable orbit, far enough away from the Earth so that there's no concerns there, and far enough away that it provides an interesting target for human exploration, because we're pushing the boundaries of human exploration. So it's either bringing back a small asteroid or retrieving a boulder off the surface of a large asteroid, something that's 100 meters plus, maybe even as big as a kilometer across, which certainly has implications for planetary defense, which I'll get into in a little bit as well. And then the explore part is, right now, the Asteroid Redirect crewed mission is a several-week mission with a crew that will go out, explore the asteroid or the boulder that's brought back, and retrieve samples and do some scientific investigations. It's what I like to kind of call first contact. The hope is that if we bring back the right type of material that's of interest to the science community and the resources community, you might have heard a little bit about asteroid mining in the press lately. There's just that first mission with the crew. Some of the objectives mention that first human mission in the mid-2020s, and also a big part of this is developing operational experience for further destinations, and finally a surface mission on Mars or to the Martian moons as a precursor to that. As Keith mentioned, we're talking about high power solar electric propulsion, and that's a technology that's key for a variety of robotic and human exploration needs. And of course, with this mission, there'll be other technologies, and Keith really hit those kind of at the end in terms of autonomous control in deep space of robotic systems. You don't have humans in the loop to do tele-robotic operations, at least for the robotic portion. You will have those for the crewed portion in cislunar space and the subsequent robotic missions that visit it. Again, enhancement of detection, tracking, and characterization, basically enabling an overall strategy to defend our planet from the impact hazard. And you can see the 4th and 5th bullets, these were actually added to the objectives based on the option B work that was done here at Langley, because for option B we can better determine the type of object that we're going to, and we can also go to something that's of a hazardous size. A less than 10-meter object basically will burn up in the Earth's atmosphere. So there is some applicability to planetary defense, but obviously a larger object that's anywhere from a quote-unquote city killer to a global catastrophe causing asteroid is a little bit more relevant. And then this last bullet about pursuing scientific and partnership interests, including the mining of asteroidal resources for commercial. And some of the commercial folks have said that if we can bring back the right type of asteroidal material, that we could advance that industry by at least a decade. By having that material there, they can start testing methods for mining and processing the materials. So again, I've kind of discussed this already, but basically JPL led the small asteroid capture mission concept, and we led the robotic boulder capture mission concept. And you can remember it as option A for asteroid, option B for boulder. There's the crewed mission, and then we also had a robotic concept integration team that kind of brought all these 3 mission segments together to do a comparative assessment. Graphically, this is what it looks like. You've got basically a solar electric propulsion module and a mission module. So this is the power and propulsion. This is the avionics and the communications and the smarts, the star trackers and all that. So this kind of forms a bus that can be used for a variety of missions. And on top of that, you've got a capture module, and that is the part that looks substantially different. There's a couple more slides, but I'll show a video of option B. But this is basically an inflatable strut and bag concept. Because a small asteroid could be a rubble pile, you need to make sure that you can encapsulate it. Versus a boulder, which you go to the surface, they're coherent or monolithic objects, and they might shed some debris, but they're not piles of loose rubble bound together by a very low gravity field. There is rubble on the surface, typically, but the boulders that we have seen from Itokawa and missions to Eros are, by all appearances, coherent objects. We won't know for sure until we get there and touch it. But if we touch it and it starts falling apart, then I think we have bigger issues for exploration of small bodies like asteroids and the Martian moons. Just to give you an idea of the size, basically half a football field for one of the solar array configurations, and of course that's what dominates this spacecraft because of the power levels. The ROSA arrays and the Ultraflex arrays are a little bit more compact because they have a circular planform, kind of a donut planform. But you're talking about a large vehicle. Give you an idea of relative size comparisons between the 2 missions. So first of all, here's a large asteroid like Itokawa that might be on the order of 200 to 500 meters across. At least greater than 100 meters is our target size. And you can see the spacecraft with a 5-meter asteroid or boulder compared to it. So this is basically option B. And depending on the orbital mechanics of the target, some targets are easier to get mass back from than others. And for a small near-Earth asteroid, like the point of departure for option A is 2009 BD, it might be somewhere between 2.5 up to about 7 meters in size. And of course, the mass grows as a function of the radius or the diameter cubed. So a little bit, as you keep growing the size, the mass goes up very quickly. So here you're talking about something about 500 tons, about the mass of the space station, or to put it in terrestrial terms, about 3 full-grown males, blue whales, bulls. So you got, I don't know if everybody remembers the Star Trek episode where they brought 2 back in a tank. That's a lot of mass that we're dealing with. You don't have the water. Well, you might, depending on the asteroid. Or you're talking about something in the 2 to 5 meter range for option B. And again, at 4 meters, you're still talking about something that's 50 tons or more. So that's actually a bull sperm whale. So just pick your whale that you want to bring back. They're both uncooperative in different ways. These guys can be spinning quite fast in terms of RPM. The larger asteroids are RP day, or they have rotation hours like Itokawa is about 12 hours. So you have fast rotation, lots of mass, less mass, lower rotation, but you do have to deal with the surface of a larger body and the minute gravity field that's there. This just shows a picture of the 2 in comparison. So here's, if we get a 10-meter small asteroid, that's what it would look like, encapsulated in the bag. And here's a 3-meter example restrained by the robotic capture system. So EVA accessibility as well as accessibility to international partners is important. I'm going to skip a little bit ahead here. This is basically just the mission profile. You're going to kind of see that in the animation I'm going to show in a little bit, but basically we go out to either a spiral or a direct injection. You go out to the asteroid, you capture it or the boulder, and you bring it back. And again, there's some characterization done. This is for the small asteroid capture option. There's a pre-deploy of the bag system, the final approach. Then you have the mechanical capture and the bag retraction around the asteroid, and then you have the spin down and detumble, which can be, that's kind of, it's been given the analogy of grabbing the bulls by the horns, because you're talking about very, very fast rotation rates. And the spacecraft is going to go for a ride for option A. Option B is similar in some respects from a mission standpoint, but we're going potentially much farther out, and we're spending longer time at the asteroid. We've looked at basically a 2x2 matrix, or a two-dimensional matrix. How you interact with the asteroid. Do you contact the parent asteroid, or do you hover? And then we've looked at a series of different robotic manipulator systems, varying from a 3 degree of freedom space frame, which you can kind of think of as your fingers. So if you're trying to grab a baseball or a softball, you need those degrees of freedom to restrain it and capture it. They also provide the push-off from the surface. We also have, based on some of the robotic servicing work that's been done, the 7 degree of freedom arms. And then we have a hybrid, and this is the one we're actually looking at right now, that combines the space frame for basically contacting the surface, attenuating the landing, or the contact, the docking, capture, whatever you want to call it. We kind of call it a landing because it's a big object we're going to. And then it stabilizes on the surface using the RCS jets on the asteroid redirect vehicle. The 7 DOF arms grab the boulder and can either lift it or hold it while the space frame push off. And we're talking about, microgravities, 10 micro-G type environments. So everything happens very slowly. There's lots of inertia, so you have to deal with that, but the accelerations are very low. The hover option is a contingency right now that we're looking at in case we have problems contacting the surface, but we can do that with all the contact options. This just shows the hybrid in a little more detail. And the one thing to mention is at the end of these robotic arms are these microspine grippers that JPL has been developing. And they're basically these appendages that have dexterous control with hundreds or thousands of little hooks. So they grab onto the crevices of the boulder when it's retrieved. And this is actually a 5-kilogram boulder, but that would represent a 500-ton boulder in space. From an acceleration standpoint, you still have the inertia of a 500-ton vehicle, but from an F equals ma, that's the equivalent. Quick heritage on the 7 degree of freedom robotic systems, basically spanning back about almost 30 years now, going up 25 years, and a variety of investments back from the Ranger days all the way to the NASA servicing arms that have been developed through DARPA. And basically leveraging about $100 million of prior investment. So with that, I'm going to show the video, which is about 3 minutes. And there's the slides up there. There's 2 closing slides, but I've kind of hit on the topics there. I'm going to kind of hit on them as we go through here too. Basically, in the animation here, we're visiting again a large near-Earth asteroid. This is actually Itokawa, which we used as a case study. We can deploy the robotic system at any point during the mission, so we can test out the robotic system. For the bag system, we have to pretty much wait because of materials issues until we get there. We do a series of flybys that characterize the surface, scope out different boulders, and then we do a series of dry runs to get comfortable with the terrain relative navigation and coming down to the surface. So this starts the boulder collection portion of it. And you can see the descent to the surface. The arrays will be positioned in such a way to minimize any contact. And you can see they're still many meters off the surface. And this is actually the descent to the surface on Itokawa depicted in real time. It's about 5 centimeters per second contact velocity. And you can see the space frame linear actuators as they attend that contact. Now the RCS system's still going to be firing to maintain a small push into the asteroid and make sure that everything's balanced. But this is sped up many, many times because this takes place about 30 minutes. And we could have up to an hour or so on the surface, depending on lighting conditions or rotation rates. But here you can see the ascent from the surface. This is artistic license in terms of the amount of debris that's kicked up. We don't know that for sure, but everything happens in a very, very slow, methodical manner. And then finally you reach altitude. After that, one key aspect of option B is that we are going to demonstrate planetary defense techniques on a relevant hazardous size object. And what we've been focusing on is what we call the enhanced gravity tractor. So it basically uses Newton's laws, the gravitational attraction, which is very, very minute, but we basically station keep in this halo orbit around the asteroid for a certain number of days, 60 to 90 days, and we can get a measurable deflection. And of course, if this is just a demonstration, if you actually use this technique, you'd have to do it for much longer to really divert an impacting asteroid. Then we bring it back to cislunar space, and the crew can visit it for the first mission and then subsequent missions. And so there's some objectives in extensibility. I've pretty much covered them. But the bottom line is the robotic boulder capture is very applicable to a wide range of stakeholders, from human exploration, Mars forward aspects, science and resources, and planetary defense. Thank you very much.